Okay, everybody, it's 3 o'clock. It's colloquium time. And this is the series, the spring series for 2021. I'm glad 2020 is over. Anyways, we have a fabulous guest speaker today. But before we get to that, I'd like to remind everybody that if you are registered, enrolled in this course as a student, you should be filling out the long form, the evaluation form, assessment form for the colloquium, and you could post those on the Canvas website under the assignments, and you should be able to do that. If you need help with that, contact me. We can figure that out. So make sure you send those in. Again, any students enrolled for the course. Well, let me introduce our guest speaker today. Well, she's not really a guest. She's resident in the department. It's our own Dr. Esther Mullens, and she's an assistant professor here in the Department of Geography. She holds a Bachelor of Science in Meteorology from the University of Reading, and she has also a PhD in Meteorology from the University of Oklahoma, 2014. Her focus areas are Earth systems and science, and geospatial analysis. And her area of expertise and her research interests delve into the areas of precipitation variability and climate dynamics and climate adaptation. So take her away, Esther.
All right. Hello, everybody. Let me just share my screen with you. Yes, I do want to stop the other one. There we go. All right.
Looking good. Okay.
Okay, wonderful. I hope you can all see that.
Yep, miss.
Great. Okay, so I was trying to decide what title to come up with here, and I decided to use what became in the end one of the highlights of the workshop that I'm going to talk to you about, which is what does extreme precipitation mean to you? And so without further ado, I need to acknowledge that this is actually, in many ways, my role in this research is minor compared to some. We have numerous collaborators. The research is actually based at the University of Oklahoma, and the specific NSF award is shown there at the bottom of the slide. And so it's PI Eleanor Martin at OU. We have collaborators across various agencies within the University of Oklahoma, including the National Severe Storms Lab, the National Weather Service, the Storm Prediction Center, NCAR, and also the South Central Climate Adaptation Science Center, which is my former employer. And so our project is known as Precip, developing a framework for seamless prediction of subseasonal to seasonal precipitation. So that's seasonal to subseasonal is sort of attempted to be highlighted in our logo that we spent quite a bit of time trying to come up with, as it turned out. So this is where we're going to go today. I was trying to come up with something to sort of go through the steps of this work, and in honor of Dr. Fick, I decided it's a track list instead of a roadmap. So if you can imagine any particular song to any one of those, they're not based on songs, sadly. But I'll introduce the reason for the research, bringing our non-academic partners together, going through the stages of the workshop that we did, kind of wrestling with issues of uncertainty and how to apply the knowledge we gained into the science. And then finally, just where this research is ultimately heading. So to start, why extreme precipitation? And I think in many ways, I think we know the answer to that already, but I wanted to show you a map of just annual average rainfall across the United States. And you can see just how variable it is. One person's average year is another person's deluge. And you can clearly see that the East is a fair bit wetter than parts of the plains in the West. But in any case, anywhere you go, if you get excessive precipitation over a period of hours to days to weeks, then you end up with issues like those shown here. This is Hurricane Harvey on the left side in Houston. And on the right side at the bottom there is the Red River, which separates Oklahoma from Texas, completely inundated after Tropical Storm Bill. So these are actually both tropical events that caused an enormous amount of rainfall over a period of days. In Houston, it was about 60 inches as an event total over a 5-day period. So that caused enormous socioeconomic issues. And in fact, when you look across from the 1980s to 2019, so about 40 years worth of data, you see this basically counts of billion-dollar events adjusted over time for flooding, severe storms, and tropical cyclones, all of which have some link to extreme precipitation. You can really see the eastern half of the United States lighting up here, especially the southeast and the south central, where there has been quite a large number of billion-dollar flood events. And not only that, we have to deal with the fact that extreme precipitation is changing with a changing climate. And this is from the National Climate Assessment. And it is based on historical data looking at trends across different parts of the United States. And you can see just based on the metrics that they're showing here. So they have a few different metrics for extreme precipitation, such as the 5-year maximum daily amount of precipitation or the 5-year 2-day amounts. In most cases, you see that the trend is upwards, particularly again in that eastern half and northeastern part of the US. So we're dealing with increasing frequency of very heavy rainfall events. But let's go back a little bit, not so much into the climate change issue, but more of a sort of the seasonal forecast issue. So weather forecasting is known most on 2 scales, one of which is the traditional 0 to 2 week time scale. This is where we use our numerical weather models with their initial conditions that forecast out to look for specific weather events that are going to impact us. Seasonal outlooks use longer term climate information, such as teleconnections, things like El Nino Southern Oscillation, sort of broader sort of patterns that we understand in the atmosphere to identify the potential for particular weather regimes to dominate. So whether it's warm or dry or something like that. But in the middle here, we have this gap, what's called the seasonal to subseasonal scale. Of around 2 weeks to 1 month time frame. And this is an area that there hasn't been a lot of research historically. And so it sort of exists in between that weather and climate scale and has been very difficult to get a good handle on. So in recent years, a lot of the focus for funding was in this gap, because as it turns out, a lot of people really care about the 2 weeks to 1 month, because it gives some lead time for a number of different sectors to begin to plan for some sort of extreme event before they get to that weather timescale. So an example of a subseasonal product is actually from the Climate Prediction Center. This is CPC, and this is a 3 to 4 week experimental outlook of the probability of precipitation being either above or below normal. So the above is in the green and the below is in the brown. This is actually a current forecast for the next 3 to 4 weeks, and you can see above average chances of rainfall in the Northeast, below average down here in Florida. Now, this is a fairly generic product. It really just says, is there going to be equal chances of rain being about where it usually is climatologically? Is it above average or is it below average, and by roughly what percent? There's not a lot of information on this. But what if we could get at extremes at this time scale? What if there is a way to identify patterns that are conducive to extreme precipitation at that 2 week to 1 month time frame? That we could sort of give an advance warning of that type of condition, which would probably be more value-added information perhaps than what is shown. So this ended up being the topic of the proposal that ultimately Eleanor Martin and again like 16 or 17 folks that are you at the time decided to go towards. We sat down one day and just kind of came up with this idea. And so we have about I think we have 6 or 7 research questions because it's a very large project. But the first research question was ultimately, what are the synoptic patterns, meaning what's this large scale meteorological patterns associated with the characteristics of extreme precipitation events in the contiguous US? What role, if any, do large scale modes of climate variability play in modulating these events? That would be something like El Nino, atmospheric teleconnections. And then how predictable are these extreme precipitation events across timescales? And 4, how do we create an informative prediction of seasonal to subseasonal extreme precipitation events for policy making and planning? And so it's really that last question that I'm going to spend most of my time on today. And all of this is a work in progress. So just before I got in a car and drove all the way over to Florida, we had a stakeholder workshop that brought together a number of folks working in professions related to, that had some sort of interest in extreme precipitation events to understand how that affects their sectors and to gather information on essentially how we can co-produce actionable research output. And this was the first of 3 planned workshops. These pictures basically just show some kind of screen grabs of this workshop. And this was in Norman, Oklahoma. So before we actually got the proposal, we did a little bit of preamble. So in the pre-proposal stage, we actually reached out to stakeholders from various professions, leveraging essentially the network that we had at the university, and especially from the South Central Climate Science Center. And so there was about almost 90 folks responded to this, and we had a vast majority from Oklahoma because that was just really where we were and where our network is densest. But ultimately, we asked them a few questions ahead of writing the proposal so that we could understand what initially might be of interest and concern, because we really wanted to get the broader impacts really kind of be a really integral part of this work. So the survey respondents indicated that the 14 to 30 day extreme precipitation kind of timescale could be useful. Here on this chart, there's basically how likely are you to use the following products. So the blue is likely, orange maybe, gray unlikely, and yellow is I don't know. So we had things like 2-week total precipitation amounts, monthly total, seasonal totals. So we noticed there's a clear increase in usability of a 2-week total versus a seasonal type of product. And then again, as you go out to looking at these very extreme extremes, so the sort of statistical extremes like 25-year, 50-year, 100-year. So then after that, we built that into the proposal. The proposal got funded. And so then we were tasked with creating this first workshop as sort of a listening session. So we reached out to the stakeholders that had taken the survey, and ultimately it's hard to get too many folks, especially since we basically budgeted in for these stakeholders to come and be fully funded to attend. So about 21 non-academic stakeholders flew into Oklahoma, and we had 15 researchers working in some government agencies and also here in Oklahoma as well. So looking at the map, you can kind of see the different geographies of the folks that attended, and also their discipline. So water resources in blue, emergency management in red, and then we actually had a few tribal environmental specialists in green, and scientists and educators in yellow. So here's back to that question. What does extreme precipitation mean to you? This was the first question we asked, and one that sort of really sticked in the memory, because it's quite interesting, the results that we got from that, depending on who you ask. And so I'm actually going to ask all of you to participate. So this is quite a bit of fun. Unfortunately, because of the way screen sharing works, you can only share one thing at a time. I will just read you what I see and maybe share the word cloud later. But the idea is that if you could go to menti.com and enter the following code that is on the screen, it's going to ask you a question. It's basically going to ask you that exact question. What does extreme precipitation mean to you? And so just answer as honestly as you can. Write 1 or 2 words that just kind of encapsulate what it means. So you can do this on your smartphone if you have it to hand. I'm just going to sort of wait a minute here and see if anything pops up. So let me know if there's a problem with accessing it. But once people start typing, it shows up. Okay, we have things are coming in. I'll just leave it a minute and then I'll summarize it for you. All right, so you can keep them coming if you want, but I'm seeing flooding coming out really high here. Deluge. I see damage, infrastructure, erosion, problem. Outlier. That's a very sort of empirical way of thinking about it. Crop loss, hurricane. Somebody put dry, so extreme doesn't always have to be wet. So yeah, climate change, hail, landslides. So thank you for your participation for that. As you could probably guess, we think about extreme precipitation more in terms of its impacts than some sort of scientific kind of way of thinking about it. So when we asked that same question to the stakeholders, this is what we identified from them. So we were kind of EM heavy. So the emergency manager perspective came out quite highly. And so flash flooding was of pretty high concern. Things like consequences, nephews. So interestingly, people were sort of going back to their memories of a specific event and something that happened during that event. Regional names for precipitation, some sciencey stuff as well, like Clausius-Clapeyron relationship. Traffic chaos was actually what I contributed because I'd been in this crazy traffic situation with heavy rain just a couple months prior. And Houston, of course, got an honorary mention because up until that point, Houston had had $1 billion flood every single year for the last 3 years. So basically, it's easier to respond to that question in terms of impacts and decisions and memories, as opposed to what I think we were hoping for, which was actual like accumulations in spatial areas. Because the reason for asking that question was to try and get at some sort of definition of extreme precipitation that we could apply in the research. So, you know, I think as scientists, we're used to dealing with numbers and trying to do things that way. And I think we were all sitting there going, okay. But amounts of concern obviously vary by location and context. So that's the other issue, is that depending on where you are geographically, it's going to make a big difference. And importantly, extreme rainfall does not necessarily mean an extreme event. So sometimes it can rain and be technically extreme, but it does not result in something damaging. And so something else that came up a lot was antecedent conditions. What is the environment like prior to the heavy rainfall event of interest? In a number of places, that's considerably important, particularly out in California, things like burn scars. What's the wildfire season been like? We had a number of quantitative guesses as to what extreme precipitation was. And again, you can see the diversity here. In many cases, it was a very short time scale, very heavy precipitation in a short time. But in a few cases, folks also iterated that when there's a kind of a long duration, kind of week to couple of weeks, consistent amount of heavy rainfall. So you get event after event after event, then that becomes a concern as well. So based on these definitions, we realized that we couldn't satisfy everybody's definition. So the next aspect was then to look at decisions. So how do these professionals make decisions in their different contexts and under what time scales? So again, to kind of look and see what type of time window would be of most benefit. We had decided upon seasonal to subseasonal, but does that jive with the information that we're getting? So obviously most people make their most critical decisions in that last few days to hours prior to the event. But there are a number of disciplines and decisions that can be made, depending on your discipline, a number of decisions that can be made pretty far ahead of that. So an example might be if you're in water resources, you might want to plan on a longer time scale. So you might start to think about conditions at that 1 month lead time or so. Most groups could see some merit to 2 weeks, but depending on the specific tasks of those professions is whether or not it was really that useful. So emergency management actually was one of the largest cohorts at this workshop, but also the ones that make their decisions at the shortest time scale. So I think one of the things moving forward is to definitely broaden out and try and engage those who do have to make decisions more at the time scale that we are looking at. So we asked them what current products and services they use. We got a lot of diverse responses, but one thing tended to come up regularly, which was relationships are important. So building trust with local agencies, such as the National Weather Service, and also having products that are known to be reliable, something that can be trusted to produce an adequate forecast that will lead to sort of some sort of degree of certainty of what could potentially happen. So many stakeholders indicated that without that trust in that group or the originator of the product, they would be less likely to use it. And so the National Weather Service for sure had a lot of trust amongst this cohort. So the next thought was, okay, how do we deal with uncertainty? How do you prepare? Do you prepare for the most likely event? Do you prepare for the most damaging event, or something in between? Again, this gives us a handle in the science side of the type of output, the type of product. Would we want to consider ranges coming from model predictions? Would we want to consider the worst case, the most likely? So the results here were diverse, but in general, we found that the worst case was something that a lot of the stakeholders were interested in. So these red boxes, these red sort of quotation type boxes are for the emergency managers. And so we had two different examples from two different people of what they're interested in. So worst case, they've got to have adaptable plans. So they're often kind of looking at what are they dealing with in the sort of glass half empty situation? What could be the worst that could happen? And then also this relationship again, relationships are important. Forecasters are not afraid to talk about uncertainty. So appreciate that honesty. Probabilistic is better than deterministic. So in other words, they want a range of possibilities rather than just one. And then from the water resources side, we had one stakeholder expressed that actually in their specific job, they're interested in the most likely output. And then another saying they're interested in the worst case. So a rainfall forecast would factor into a specific management plan. So depending on what the rainfall forecast was, that kind of tells them what plan they need to implement. And oftentimes when they're evaluating whether their plans succeeded or failed, they use these very high impact worst case events as a benchmark for that. So again, you also see not only do we have a geographic diversity in what extreme precipitation means, but also how you would prepare for it. Okay. So the next question, how reliable would you want any precipitation product coming out of this research to be in order to be trustworthy? So most participants indicated that any forecast product that's only 50% accurate, even if it has a good lead time, so 2 weeks to a month, is really not very usable. But once you got to about 75%, so it correctly predicted, like, 3 out of 4 times at those same timescales, and that sort of got the interest going a little bit more. And again, the importance of having a good track record and trust relationship with those product creators. And so most of our cohort didn't really see a merit for a seasonal time frame, really more of a sub-seasonal, so 2 to 4 weeks. So here's the challenge, and I'll talk about this a little bit more soon. But when you get to that, you think 50% accuracy, in the sort of few days forecast, you would hope that something would exceed that level of reliability. And then that is indeed true. This is a diagram of essentially it's giving you a sense of how correlated is a forecast of, in this case, geopotential height, so kind of circulation patterns in the atmosphere, compared to what actually happened. And you can, and on the bottom here is year, so you can see 1981 at the bottom all the way to 2010. And so what is evident is that forecast skill has improved with time, but that forecast skill is lower the longer in the future you are predicting. So you see at day 10 there, your forecast skill, your correlation essentially with this metric is really pretty low. So our biggest challenge is whether or not we can actually even get to the level of predictability that is necessary to be really truly usable. So the last part of the workshop, we kind of had a little bit of I don't know whether you can call it fun, given that we're talking about disasters, but we wanted to kind of go through a sort of scenario, a role playing. And we used the Baton Rouge flood of 2016. So here's a rather horrific image of the results of that flood. Really did a lot of damage to that region. It was something like 30 inches in a couple of days in August. So the goal was to see how participants interpreted and translated the forecast product information in their decision contexts. So how do they perceive the graphics? How would they use them? All the way from 3 months to 1 day. And I'm going to not talk about the 3 months because, again, I think most of our stakeholders really didn't see much utility in it. So this was the scenario. The city is planning a ladies golf tournament for the date that will ultimately be co-timed with a flood. They don't know it yet. This has been planned months in advance, and of course the town wants to have it because it confers economic benefit. However, as you monitor the impending weather changes, what decisions must you make to protect lives and also to kind of keep the mayor happy, because you've got these competing issues at play. And so we designed this to try and at least be somewhat relevant to the types of decisions that the stakeholders make on a day-to-day basis. So we started out by presenting them with a sub-seasonal graphic. So this time scale is about a month. And so you can see here that, again, this above and below average definitions, this green area indicates the chances of above average rainfall in that zone. And this is the kind of responses we got when stakeholders were presented with that information. So one said, cool, looks like it will be rainy. So not, yeah. How much actual rain has fallen in the past few months? Figure is not quantitative enough to be thinking of extremes, which is fair. It really is just, is it going to be above or below average, and by what possible amount? And I can't actually see what that one says because I have a chat box in the way. So, I think something along the lines, they're used to, this type of thing. Slightly more than average isn't going to be a big deal. Risk has shifted upstream from the Mississippi River versus the initial 3-month plot. So they were interpreting the expansion of the above average as a sort of a risk change. And another person said, would not think to check this product unless explained by a trusted source. So for the most part, it doesn't factor. Then we got to a 5-day lead time. And this is this diagram is a quantitative precipitation forecast. So you're looking really the redder the contour fill there, the heavier the rainfall. And so you can see across the Northern Gulf, there's this bullseye of about 9 inches of rainfall, like just a little bit south and west of where Baton Rouge is located, which is in eastern Louisiana. So now the interest increases. So people are concerned, is that an area that evacuates? If that area shifts west, that's my concern. So if that bullseye of high precipitation comes right over, what is the expected intensity? So more information is desired. And then, this time scale, critical decisions are starting to get made, who to bring in to manage the situation. And you begin to start to talk to first responders, or the event organizers need to know about the possible change. And of course, emergency operations centers, again, reflecting the emergency management viewpoint. So ultimately, one of the things we learned from that is that these sub-seasonal products, they're just not used as much by this particular group. And there was more confidence as you got closer, as you can imagine, but also seeing that quantitative information. So limited utility of greater than 1 month forecast information. We need to broaden our cohort to look at those who do use that information, so that 1 month to 2 weeks, less familiarity with the seasonal products. So that was good actually to know, because we had representatives from the Climate Prediction Center there who were quite interested to sort of get that feedback on their product. And the relationship is vital. And the extreme precipitation is highly contextual. So we sort of came out with this workshop realizing that when you engage outside of the academic sphere, things become more complicated. Ultimately, I think it's a really good thing. But you realize that, especially looking at extremes over this sort of scale, the entire United States, that we have our work cut out for us. So products really do need to think about producing a range of scenarios and providing some sort of quantitative information as much as is possible, given the issues with predictability. And ultimately, the forecast product does need to be accurate to be trusted. But the one thing, despite the fact that we end up with, in some ways, more questions than answers, what was really nice about this process was that we genuinely got to know one another. And so this was some of the feedback that came out of that first workshop, which was that it was a bridge to help those outside of academia, but really, who would be using this stuff, help us understand your needs, as well as at the same time help you understand what we need. And that face-to-face engagement builds that trust. And the ivory tower opens its doors. So yeah, the ultimate, if nothing else, we are building trust with a community that we hope to continue to engage with, so that these products don't just get put on the shelf at the end of the day. So the next part I'll talk about is a little bit more about the basic research, the scientific part. And if I sort of scramble around trying to explain a few things, it's because this is actually the part that I'm not so heavily involved with. My work really has focused on that broader impact stakeholder engagement side. So we, let's see if I can move this thing around. There we go. So the first thing was the definition of extremes. Without that coming up with some sort of definition, we really couldn't go any further in the research. And obviously the definitions that we got through our listening sessions were very varied. So we ended up taking an approach where we regionalized the United States. You can see here these regions, and essentially kind of analyzed events for those individual regions. Let's see, hold on. Okay, yeah. So the definition that ended up being used for extremes was ultimately anything greater than a 95th percentile over a 14-day accumulation in a moving window. So this is not looking at short time scale events. This is looking at that consistent heavy amounts over a decently long period of time. Also, it has to have a minimum spatial extent. So we're looking at the spatial distribution of those events, not just whether or not they met this threshold in terms of magnitude. As a sort of check on this work, one of the graduate students at OU looks specifically at flood reports associated with these events versus any other random 14-day period of time, and does see that these events are linked to substantially higher numbers of flood and flash flood reports, as you would imagine, and that's true of anywhere. This is just the example for that Southeast region. So not only do you have to kind of come up with a minimum threshold, the group decided to kind of come up with essentially a definition that can change with time. So flexible may not be the best word here, but something that is adaptable perhaps, because as precipitation extremes are changing in a changing climate, there needs to be some way to account for that. You know, what is extreme back in the past may not be quite so extreme now. So this is an example of a quantile regression. So instead of just calculating a 95th percentile of the observed precipitation at each grid point across the whole United States, and taking that one value, which is the green line, instead this quantile regression calculates a 95th percentile that can change over time, and as you can see, it increases quite a bit into the more recent period. That accounts for the non-stationarity of precipitation. The next thing is then to look spatially, and so this is an example of just an individual event. And on the top left, that's the precipitation amounts over that time frame. The top right is the quantile regression, where it indicates that the event met the threshold for extreme. And then there was an additional check that looks at essentially like how many days is the precipitation above a certain value, and then only retains cases where you have that above normal precipitation for at least 7 days out of that 14 days. So these different criteria then allow for both an intensity and a duration, which duration is a very important criteria for extremes. And ultimately that green area is what you end up with. So for every single event, that is the process that was taken. And those events are actually in a data set now. That was another student's master's project to basically come up with that event case data set. So when you look across the whole contiguous US, you can see the frequency of these events over essentially the past century. And you can see certain highlighted areas where there are more of these large, long duration events than others. But there is one fairly major caveat. When you look around the edges of this domain, you see that the values rapidly tail off because there's no data over the oceans. So the problem is places like Florida are underrepresented because basically hardly any events will meet that minimum spatial criteria. And so there's kind of a bit of a problem at the boundaries, potentially. So the next part is to examine the characteristic meteorology. So we're trying to figure out, okay, is there any potentially predictable signals in the meteorology? And just by way of interest, it was noted that quite a lot of these 14-day extremes are related to atmospheric river activity, not only in the more well-known regions such as the Pacific Northwest, but also in the Southeast United States. So in this case, about twice as many of these extreme events have an AR, atmospheric river, as not. And this plot in the bottom left just kind of depicts an example of integrated vapor transport, which is a function of the amount of precipitable water and the winds. So this is an example of a AR-like feature over the southeastern US. So that work was done to identify synoptic precursor conditions. And this is an example for the Southeast US. So this is between 10 and 6 and 5 and 1 days prior to the onset of the heavy precipitation event. And this is a measure of circulation, geopotential heights and measure of circulation. So you can see not a whole lot, as it turns out, because there isn't really a strong signal other than the fact that ahead of these events, there's some indication that there is an active storm track across the southern tier of the United States. There aren't that many significant anomalies in height. So that obviously leads to some problems with predictability, because if there aren't really a lot of strong signals, it's hard to sort of build a model around that. The antecedent environment is another aspect where there's some ongoing research. And in this case is to look at whiplash, going from a drought month to a wet month. And this analysis was done over the South Central US. So basically, if this wet, dry, wet has to be 1 month being below 25th percentile in precipitation accumulation and the next month being above the 75th. And so when you can do a density of analysis of that, what you end up seeing is that it kind of follows the pattern of precipitation in that region. So the spring months indicate there's a little bit of higher variability potentially, and September really sticks out as well. So some of this work is trying to get at these different features and in time, hopefully integrating it all together. So the last part is, where do we go from here? So we have the stakeholder input, we have the work that's ongoing. So this figure right here, this is a Northeast synoptic archetype for extreme 14-day rainfall events across the northeastern part of the United States. The blue area is essentially like a trough. It's a low pressure. And the red area is a high pressure. And so it's a fairly, what looks like a reasonably strong signal there for a certain synoptic pattern that is conducive to extreme precipitation in the Northeast US. And so the group analyzed the congruence of essentially above a minimum threshold and determined the number of events that met that threshold or not. And when doing that analysis, not only for this region in the Northeast, but across all of the different regions in the US, the results are definitely problematic. So what I'm showing here is the probability of detection, POD, just indicates the number of events that were successfully forecast versus the sort of compares it to the ones that were forecasted in error, and then something called the false alarm rate, which kind of indicates how many times something was forecasted that didn't happen. So in the end, the detectability of these events is pretty low. And the false alarms are very high, which means that these synoptic conditions can explain some heavy precipitation events, but they also miss a whole lot. Or you can have that type of synoptic pattern and not have a heavy precipitation event. And adding in something like precipitable water, seeing whether there's any distinguishing factors in higher or lower precipitable water, actually in many cases decreases the probability of detection. So we have a predictability problem, and work by an undergraduate student that was presented just recently analyzed a lot of dynamical seasonal prediction models, looking at these 14-day extreme events for a subset, so not the entire database, but indicated there was no convincing regional or seasonal model skill. And so this this kind of animated graphic shows a extreme precipitation event on the top right. So just kind of how it evolved over a 14-day period. And so each different day has different amounts, some more, some less. And the other plots show lead times at different lead times. So the top left is the longest lead time, top right is second longest, and then the bottom two are closer lead times. And so you see as each day goes through, there's no real consistency from lead time to lead time. I mean, in some cases it does pick something up well in advance, but maybe then the next few days it disappears again. So whilst there's some evidence of potential skill, a further analysis is necessary to determine exactly how much skill is possible from these dynamical models. So the next steps are really to do that multi-scale assessment of seasonal to sub-seasonal predictability in these events through all of these what's called national multi-model ensemble models, which are a whole bunch of seasonal climate models. And then the next step is to actually look at statistical predictability. One of the goals of the research was to develop a statistical model that would, so not only would you have the dynamical side, the model, the actual full atmosphere model, but you could also develop statistical models. But that implies that we know enough about the atmospheric processes to be able to have the right kind of input to those models. So that's going to involve some machine learning work. And then subsequently, we're continuing to build in this stakeholder engagement throughout this process. And so again, building that trust. And hopefully recruiting more stakeholders, particularly those who make decisions on that sub-seasonal timescale. We started a regular newsletter, and we aim to begin some online seminars and discussions, because the COVID era unfortunately has delayed this further interaction. So the hope is to have the next workshop this year. It was supposed to be last year, but we'll see what happens. And the theme will be product development. This is a nice graphic that one of the graduate students came up with of something that maybe if we can ever get the predictability to work out, we can get. So takeaways, I'm running out of time here, but basically talk to each other is our big thing. Building trust and continuing to iterate this process, not only from the academic side, but also engaging those who will hopefully use this, the output from this research. So thank you very much, everyone.
Thank you very much, Esther. I have a question to start out. So before anybody else does, I'd like to, I'm not a physical geographer, but are there places in, let's say, North America that are completely just impossible to use sub-seasonal types of predictability models? This just won't work. If you could cookie cut those out and just concentrate on areas perhaps that it might prove to be useful, is that possible? Because I noticed that over time, your predictions seem to be getting better, right? That one graph indicated that, correct?
Mm-hmm.
And is there particular places, let's say within North America, where we see an acceptable level being approached? At least we're starting to get to a threshold now in these areas, but the rest of it, forget it. These areas the models will never do very well. Is there a distinction between areas where the model will perhaps do well in the future based on that increase we see in the accuracy, and will there be places outside where the model is just absolutely no sub-seasonal model will work?
Yeah, I mean, in many cases, the seasonal scale, at least, is the forecasts at that scale heavily rely on teleconnection patterns, so known climate variability and its relationship to precipitation or temperature in a given region. So if a region has a complex relationship to those types of teleconnections, or it's dominated by multiple different teleconnections, it can be hard to get a good sense of predictability in that area. One example is actually the South Central United States that has both an impact from Pacific and Atlantic modes of variability, and depending what phases they're in, it can. Right. Yeah, so at the sub-seasonal scale, though, it's not just about those teleconnections, it's also about these other types of patterns that can sometimes get locked in, just how many low pressure systems come across, that sort of thing. And so I think, that would be a good thing to talk to the team about, is to what degree we're going to pursue perhaps regionalizing this analysis, so that, the goal is to get a product that is nationally inclusive, at least across the continental US, but that it may be limited. One of the other caveats is the size of these events. They have to be large spatial events. So and part of the reason for having the large spatial events is that those smaller ones, like so issues with mountains and things like that, are just much more difficult and dominated by smaller scale processes. But that is a good point.
Oh, I open the floor up for questions here.
Okay, Tim, I will jump in to encourage others to do the same. First of all, thank you, Esther, and I believe that I missed Heidi pointing out that you were actually relocated to Alum Bay there. Sorry about that. This could be pedantry at its worst, and I think it might develop into something a little bit more. In one of the very first maps you showed of the United States, you actually had a graph from NOAA, I believe, which surprised me, that said this was annual rainfall in the United States. And as a representative of the country north of the border here, and I know Tim will agree, that in fact some of the big events are actually not rain, they're snow. So I'm presuming that was precipitation, and from a hydrologist point of view, you're using those terms interchangeably here. Now, if you're talking about the southeastern United States, that's not an issue. But if you're talking about places like, and going back to the stakeholders, and you notice that the water resources people were very much more interested in longer term, because the rivers are responding, got a longer lag time than instant response to the environment. And if that precipitation comes in the form of snow, then in fact the response that you see in the river may well be lagged by months. All right, so their interest is going to be slightly different. Now, I know that your stakeholder meeting was sort of focused a little bit on the Southeast. But I mean, right now, I don't know what actually happened, but last night they were forecasting up to 8 feet of snow in the Sierra Nevadas. So that's a major rainfall event coming down into the Central Valley of California. But that snow could be staying up there until, well, May, right? And that wouldn't be picked up in your modeling. So I think that you know, the stakeholders, that's interesting because they're going to have different timescales they're interested in because of the time lags, and the time lag then is related to the type of precipitation. And I can see Tim nodding there because you get these blimmin' great big, I forgot what the term is now, but you know, the lake snow effect, these great streams that come off of the Great Lakes and will dump on Buffalo for days and days and cause immediate problems. I mean, with the roads, there'll be problems with the interstates and so forth. But that snow won't appear as a hydrologic issue and an extreme event until some time later. And then going back even further in my history, the biggest flood events in the Pacific Northwest are caused by rain falling on snow.
Mm-hmm.
All right, so those are your outliers there. So I was just you know, pedantry here in terms of you got to separate precipitation from rainfall. You know, if you're going to talk about the total amount, let's call it precipitation, not rainfall. If you're talking about rainfall, let's exclude snow.
Yeah, no, you're correct. And I think, to be honest, that's just a function of my lack of sleep with a baby.
Oh, no, that is
As to, you know, the rainfall versus precipitation, because you're exactly right. And in fact, what I mean is precipitation. I don't mean rainfall.
That does then land that issue that, okay, yeah, that if it's snow, that problem is still in the landscape. It's still in the system. It's not.
Yes.
And
yes,
then,
it is. And I should have also mentioned, and this is a rather large caveat of the work, is that it really focuses on atmospheric processes. We did not design it to consider hydrology. And I think that's also where the disconnect comes in with what the stakeholders are interested in and the kinds of things we were hearing, because it's so much based on the surface. And we did actually do another role play. So the one I showed you was the south one that I was involved with, but the other role play actually was for a more northern location, and it incorporated snowfall considerations as well in the decision process. And so I have less familiarity with that particular one, but yes, it's hugely complicated because our 14 days, yeah, it's based on precipitation that fell over that time. And so the lagged response in the hydrology is not something that
right,
that is really,
I mean, and it was apparent. It was, I'm just sort of saying that we have to be very careful, as always, with definitions like you started off with, right?
mm-hmm.
And just one while I'm at it, just the sort of the modeling perspective, and I very much like your diagram with your predictability, or your ability to predict versus time out, mm-hmm. and that, so all the sort of dynamic models are pretty good for 1 day, 2 days, 3 days, and you know, I'm always warning Maryland, don't believe anything that says 10 days ahead. It's not, you know. And then that break, and then you've got the more as you say, teleconnections and type, which give you that. But I mean, that's a change as we go from the type of modeling too, right? I mean, go from the dynamic, the physical meteorology through to the more sort of stochastic, probabilistic type of modeling. And you know, I wonder if you're ever going to fill that gap, because the atmosphere is a nonlinear dynamic system, right? And so, yeah, you can get it pretty accurately one time period ahead, but mm-hmm. then things start to just go crazy. And so until when you go so far ahead, all you're left with is just probabilities of being in different states.
Yeah, I mean, it's interesting that there's sort of a lot of the models that run on that time scale, they're climate models, but they've been adapted with to sort of run like weather models. They focus on initial conditions more than a traditional like climate change experiment would. Okay. And yeah, I think there is, it's a forecast hole for a reason. I think there is the expectation that it can be solved in time, and there's a lot of work on it.
Yeah.
But yeah, it is in that spot of significant. So statistical models are often used to try and kind of find these relationships and see if there's any way to kind of use a statistical approach as opposed to using the fully, you know.
But it's interesting that that might be where the most demand is right now for forecasts. So paradox. Okay, thanks a lot, Esther.
Okay, it's well, anybody else? Quick question, real quick. Well, it's 4 o'clock, and we'll call it here. Some people will have to leave the meeting, and appreciate everybody coming. And next, Esther, thank you so much. You did a wonderful job. And if you don't mind sticking on, I have another question that I'd like to be, don't want to make you work more, but I have another question that I would like to ask. But anybody, we'll see you. Thanks for coming, everybody. Thank you so much for attending. It's been a great success. Attendance has been good. Esther, I have a question. It's related to what Pete was talking about. I think I thought about flash floods, and one of the questions, when you posed the question of what is extreme precipitation to me, and it was flash flood. That was the thing I said to myself, because it's not just flood, but it's flash flood.
Right.
I lived in Arizona for a while, and I thought about we get an inch of rain in one day during the monsoon season, and what happens? The arroyos flood, and you can't drive across town because some of the arroyos will block the traffic. But it's what happens that day is what really, it produces the flash flood. Now, in some places, Pete was talking about the snow melt. I was thinking about, if you look at the map of precipitation, North Georgia, the Carolina, that area, there's a real dark green spot where we're getting like 50 inches of rainfall. If you have an extreme event in the mountain areas, and then you had snow on top of that from the season that was happening prior to that, so you got an excessive snowfall year, and then you get an excessive rainfall year on top of that. So you got months lag, but by the time the snow melts and all that, you might have a flash flood event that's coming somewhere in an area downstream in a tributary where all these rivers are kind of, the water's flowing in that direction, and that might be months away. Now, that's very different from the pattern in Arizona, and that's where sort of I was talking about eliminating some places which just are not going to, sub-seasonal stuff won't work. Like maybe Southwest, just not going to work, but we can see it. And if you can incorporate those hydrological or whatever fluvial hydrological elements into the model, that would maybe perhaps increase the accuracy of those models in those particular regions. But anyways, what do you think of that?
Yeah, I mean, I think it just it continues to be the issue. And when we finished this workshop, we had got so many interesting insights into the regional issues that were experienced. In fact, one of our number was from Arizona, and talked about kind of the flashiness of the region. And so, the researchers are sitting there and like, how do we basically like, oh, okay, we've got a lot of work to do, and we've got a lot to understand from each other, and we cannot get at all the things that people want to get at here. And so I think when it comes to the project, it was conceived as creating a national product, and to do that you have to sort of you can't go, you just have to sort of pare back, but that does mean, I mean, maybe then it has limited utility to any individual person. So I think those are questions that honestly I'd like to discuss with the team, as to how this is all going to be integrated at the end of the 5-year plan to something that is going to, at least in some way, shape or form, satisfy some sort of, it's going to have some sort of benefit. And even if in the end the benefit is that we built trust with a group of people that aren't used to being brought into academic analysis.
That's true.
So
and if you find out that the sub-seasonal doesn't work in 90% of the regions, it's not really going to be a viable method. But those 10% you might identify, those might be places that could benefit from this research. And I think it's wonderful.
Mhm.
Early, kind of early warning. I don't want to say, I don't know if that's a great term to use, but at least a lag warning, you know, that something might be amiss in this area. So watch out.
Yeah.
That's
Yeah. I
really,
mean,
really useful.
we had representation from the Climate Prediction Center there, and actually I think a year or so ago, they started a product where they were doing a sort of a hazard kind of an experimental product which shows you areas where there could be heavy precipitation in a 8 to 14 day window. So they what's nice about having them on board is that they are the ones that ultimately operationalize these forecasts into things that everybody gets to see. So that way, if we do come up with anything that can be translated into that, then hopefully they'll be able to do it. So yeah, I mean, it's kind of a high risk, high reward type of project. There's a lot of angles to it.
Yeah, just jumping in there. There's a lot. I mean, there's a lot of angles, and in many ways, you know, you're probably going to have to chop it up. And you can take the same approach, but for different people, for different stakeholders, they're going, as you say, as you pointed out quite rightly, they're going to want different things. They're going to want it over different time periods. And I say geographically, you know, one of the things in Canada was always, what's the accumulated snow? What's their snow accumulation? Because when that temperature goes above zero, that lot's going to go, right? So is it going to be a big snow melt event or not? So, you know, when the snow fell, yes, it had disruption, just like you said, with traffic chaos and roads being blocked and all this sort of thing, accidents. But the hydrologic effect is building up. This is building up. This is building up.
Yeah,
he did something.
You're right. It's very ambitious, and it's obviously something, you know, that I struggle with every time we give a talk. What is extreme precipitation? And basically, I palm it off by saying, well, whatever you want it to be, you tell me. And
yeah. I mean, the scientists were going with numbers. Other people were going with stories. Other people were going with something that's like memories. It was very interesting. But yeah, I don't know. My role mostly is within that context of engaging with the non-academic partners. So in terms of the research, what I do see is that, I mean, basically the research is funding a lot of graduate students, a lot of PhD students and master's students. And
of itself, yeah, right.
And so it's sort of become, it's become, and that's you know, when you have something with 16 people on it, putting it together is going to be,
it's going to be hard to put it together because of the nature we just spoke about. It's going to tend to want to box it up and fractionate it. And then when people aren't meeting, they're going to go off in their own direction.
Yeah. So, but hopefully, you know, I think that what's coming out of it is very interesting, and continuing that engagement, even if at the end we're like, well, sorry, we didn't get to answer that grand question, but we did at least get to meet you and understand your needs, and maybe there's some other work we can do on a regional scale that might, you know, so that's kind of, it's been good for me because now at least, you know, I haven't seen these folks for a couple of years, but it would be nice, you know, if I have a question, a research question or something, being able to have a group of folks outside of academia is quite nice. Be able to lean on their expertise.
I know one other thing I wanted to talk about, which I kind of didn't say I took exception to, but you had your non-stationary extreme, you know, you showed the time series with that lot jumping up in, but I mean, what's extreme, I think, is what you designed for, really, right? I remember I met a guy at one of these alumni dues, you know, where you schmooze with people, and he was responsible, his company got the contract for building the little culverts, the weirs where the water goes down the drains here. How big a hole do you make to take the water away, right? I mean, obviously you made a bloody great big hole in the gutter at the side of the road, you'd be able to take away Niagara Falls, but it would be so expensive. So he said, you know, they design it for a 5-year return period event, so it can handle everything. But once every 5 years, it's gonna flood. And he wanted me to tell him why the government had now made those bigger and therefore more expensive for him to make. And I said, well, because what is a 5-year event you know, in terms of risk extreme, has become has actually become more common. It's no longer the 5-year event. If you want that sidewalk to flood once every 5 years, only once every 5 years, you're going to have to make a bigger hole, and that's why you're being asked to make. I said it's climate change, and you know, the old boy, he wasn't very happy about that answer. But you know, an extreme is relative to what you're designing for. Extreme in terms of a flood, extreme if it's geomorphology in terms of soil erosion, right? I mean, it's just when the intensity gets over a certain amount. So I wonder about putting that line through. You're kind of minimizing. You say it's non-stationary, and I agree, but I mean, you're kind of minimizing the fact that the extremes have changed. Extreme is defined by what we do.
Oh, so yeah, I mean, I see. So I guess, yeah, I mean, over time, the minimum threshold for inclusion of an event increases. So
yeah,
the event has to be higher in magnitude in order to be included.
Right, and that's a little dangerous, because you know, you got Britain in the background there. I mean, a lot of our infrastructure was designed for Victorian conditions, right? And now we're finding we get more intense, more frequently more intense rainfalls, and it can't handle it anymore. Right, so that's what makes it kind of extreme.
Yeah, I mean, I see your point to that. I mean, ultimately, you would end up with more events in the latter period than the early period using a more traditional definition. And right. Yeah. You know, I don't know. I would have to talk to the folks involved as to the original rationale for that non-stationarity. I think the idea was what is significantly unusual for that period of time.
Yeah. So then what you'd be doing, you would be recording what the value of the 90th percentile is. In 1920 to 1940, it was this, but from 1940 to 1970, it went up to that. You know, and so then you're actually recording what's happened to an event with a particular return period. But in most cases, as humans, we're designing for a particular discharge, a particular rainfall, all right, and that's actually becoming more common. So that, you know, whereas that the other one is is flipping it.
Yeah, I think that I'm wondering from the forecast perspective whether it's an issue of we're just in a different regime now than we were. And so if you're looking at seasonal to sub-seasonal timescales, if your threshold for inclusion is lower, I don't know. Yeah, that's an interesting.
Yeah, I mean, I think your threshold for inclusion is to find what you're interested in, which would be meters per hour or total amount of snow accumulated or something, right? Rather than saying, well, this used to be included in the 1930s because things were drier. That was extreme, and now it's wetter, and we're saying this is extreme. I mean, I think that extreme is only a function of really what we want to do with it as humans, particularly given the group that you're working with, stakeholders, right?
Yeah.
People want flooding in rivers, dams breaking, culverts being full up. Those all rely on hard numbers on how frequent, you know, that event is.
Right. And they're all different numbers too. So, and that's where I think, you know, in the end, it's just a series of decisions that you know, we got ourselves into something that, you know, it's a very complicated area. And so, and I think what makes it complicated is the scale. Like if we were doing this analysis for, I don't know, some county or small region, then we kind of have a clearer definition because.
And I mean, it's the same with drainage basins, you know. The smaller the area, then the more likely you are to get flash flooding, you know, in the response, but you're not going to get flash flooding in the Mississippi. I mean, it's a totally different system that you're dealing with. So,
yeah. And I think that's the thing. I think when we listen to the stakeholders, like I say, we're listening to the on the ground problems.
Yeah.
When we're in our research mode, we are dealing with the atmosphere because it's a whole bunch of meteorologists. So, you know, that
we feel more comfortable in dealing with that. Yeah.
So yeah, I mean,
All right. Well, thanks once again. I appreciate the time, particularly now. You probably wish you were going to sleep and catching a nap. This husband of yours to to get his act together and
he can hear you.
I can see his picture right here in front of me. That's why I said it. The good news is that it's just his picture. He's not giving me the finger or anything on the screen. So he's
a very dedicated dad.
There he goes.
He often takes more of the night than I do.
All right. Thanks a lot, Esther.
All right. Take care.
Thank you, Pete.